Okay, let's take a look at this problem that we had where we had the teachers and we had the aides, and we were trying to minimize the cost, and we were told a couple things. We were told, first of all, that the total number of teachers plus aides have to be less than or equal to 50. So we graphed that line there as the boundary for that inequality region. We were also told that the number of teachers and aides in total has to be greater than or equal to 20. So now we graph that line, x plus y is greater than or equal, x plus y is equal to 20. And now we know the region is going to be in between these two lines here. We were also told that the number of teachers has to be greater than or equal to 12, which means that we graph, because we're putting teachers down on the x-axis and aides on the y-axis, we graph the line x is equal to 12, and we know that now we have to be to the right of that line. So now our region is getting a little bit smaller and more clearly defined. And then we also have, we're told that the number of teachers has to be at least as great as half the number of aides. So we would say x is greater than or equal to y over 2, which means that what we'll graph is x is equal to y over 2, or y is equal to 2x. And we know again that because the y value has to be less, that we're going to be below that. So what that gives us is this shaded region right here. And that's our feasible region. And we know we want to be low in the region because we want to minimize our costs. So we're pretty surely going to be at one of the vertices of this thing, and we'll just mark those as A, B, C, and D, and E. And we're pretty sure we're going to end up being in either A, B, C, or D, and most likely B or C. Okay, so our objective function, the thing we're trying to minimize in this case, or in other cases it would be to maximize, our objective function is the cost. And we're told that the salary has to be, for each teacher, is $40,000 and $25,000 for each aide, and we're going to therefore divide everything through by 10,000. We'll get the same line and say 4x plus 2.5y is equal to the cost. We don't know what that cost is, but what we do know is the slope of that, and that's determined by the relationship between the teacher's salaries and the salaries of the aides. So for example, if we were to solve this equation here, our objective equation, in terms of y, we would get that y is equal to cost divided by 2.5 minus 4x divided by 2.5, which would give us negative 8/5 x as our slope. And so when we graph that line, and what we'll do is we'll use this slider here to control the total cost. So right now we'll say 4x plus 2.5y is equal to 90, and that gives us this line right here. Let's make it a little more visible. And we'll make it a little thicker, and we'll make it, let's say, dashed. Okay, so now again, as we move that line, we can see that the slope stays the same. And what's pretty clear is that where we're first engaging the feasible region is right here at this point B. And that means that's where we're going to have our lowest possible cost. And point B represents 12 teachers and 8 aides. And when we plug that in, we're going to get that the total cost is going to be equal to the 12 teachers times 4, which is 48, plus 2.5 times the number of aides. So we have 48 plus 20, or a cost of 68. Now we're also told that, and that represents $680,000 in this case. We also were asked to draw the line representing a total cost of 1.2 million, which means that 4x plus 2.5y would have to equal 120, and that's this line right here. And that line, of course, just represents our objective function set to equal 120. So again, what we see here is that because of the slope of this line, that we will hit this at point B. Now, if the slope changed, if it flattened a little bit, we could see that we might hit at point C, which would mean that we'd hire 20 teachers and no aides, as opposed to, in this case, 12 teachers and 8 aides. So again, we went through, we graphed the boundary regions, which are our constraints. Even though they're given to us as inequalities, we graph the lines, and we just stay mindful of which side of each line we're going to be on. So here we had x plus y is equal to 50. We're below that. X plus y is greater than or equal to 20. We're above that. X is greater than or equal to 12, so we're to the right of this line, x equals 12. And x is greater than y over 2. So right here is the line x is equal to y over 2, and since x is greater, we have to be to the right of that. We also were told that all the values have to be positive for teachers and aides, so we're above the axis, the y-axis and the x-axis. We're going to be above or to the right of those. Okay, that's how we found our optimal point here, point B.